Hello, and welcome to another video of mine. This time, as you can probably deduce from the title of the video, I will be trying to make an ARM-based laptop whilst recycling old parts and creating new circuits to make it all work together. This is going to be a pretty specific, or one might say one-of-a-kind build, but most of the tricks I will show you should help you too if you want to make something similar. However, as this project is a bit more complex than I have originally imagined, and as I want to focus more on the theory side of things, I will be splitting up this project into multiple videos. In this one, I will explain the current plan I have in mind for my build and show how to make a relatively simple power management circuit that automatically switches the main power source of the whole laptop from a battery to a power adapter when one is connected. As you also might have noticed, I have been filming in a completely different room. In the last few months, I've moved to Germany for university studies, so I have been pretty busy, which led to a more theory-focused video, as you will see. Currently, I don't have many or most of my tools, like my 3D printers or my desktop PC, so the initial few videos will likely be a bit more scuffed than usual. This is all not negative though, since I finally have the opportunity to order stuff internationally, for example PCBs or even stuff from AliExpress, Amazon, so I hope the following projects are going to be a bit more polished or a bit more colorful. Let's start with how this idea even came to mind. As you can see, the laptop I am holding right now, best to say it was a fully functional laptop at some point. About a month after the warranty ended, a brownout created a voltage spike, frying and shorting the CPU and burning a thick copper paste on the laptop to smoke. This meant that I was just left with e-waste, or better explained, a useless brick. Or so I thought. Although the motherboard was basically completely useless, there was much to be harvested. Most modern laptops use EDP or embedded DisplayPort to interface between the motherboard and the LCD. This means that in most cases you can source display driver boards that can convert a simple HDMI signal to EDP and hence make the LCD usable. In my case, I was able to get a driver board from AliExpress, and after some waiting, I had a nice 1600p display with a 100% sRGB color gamut. This itself is a pretty big motivation force already. The keyboard, the trackpad and the other more passive components are also fine though. This means that the only thing that needs changing is the main motherboard. In this case I will be using an Orange Pi 5, but you can realistically use whatever single board computer you want, an x86 based one like the Rexa X4, an ARM-based one like the Raspberry Pi, or even a RISC-V based board like Milk-V Mars. The parts I mentioned are mostly off-the-shelf parts, as you can see, but they are not really equipped with battery management circuitries most of the time. This means that to make a DIY laptop are actually portable, a custom power management circuit must be used. To get an idea how a normal laptop automatically switches between battery power and the power adapter, we need to first look at different types of laptops and their motherboards. There are a lot of schematics for older and also sometimes modern laptops online, and some research makes it pretty clear that most of the time laptops use the same kind of chip. So most of the time laptops use a variant of the BQ series, SM-bus 1-to-4 cell buck battery charge controller, which was also the case on my laptop, which used the BQ24800 IC. Now what does this IC do exactly? To understand that, we need to take a look at its datasheet. As the datasheet says, this IC is responsible for charging the battery and also managing power dynamically. This dynamic power management is pretty important when it comes to high-power laptops. Let's imagine a situation like this. We have a laptop that can draw about 55 watts on full load, and the nominal battery charging speed is around 50 watts. This wouldn't be an issue if the power adapter could supply more than 105 watts, but most laptop manufacturers would give this laptop about a 65 watt power adapter in the name of cost cutting and also sometimes efficiency. In this case, the 65 watt adapter needs to be routed dynamically to the place where it's needed the most, which this IC can do pretty much automatically on its own. Well, if this chip is so great, why not just use it here too? Well, that would have been a great option, but I do not honestly think that everybody that wants to dip their toes into such a project have the equipment or the experience to solder this 5mm by 5mm 7-pin chip. At least I know I don't have both of those. Additionally, you cannot use this IC just on its own. You need to connect it to some kind of SM bus master in order to change its settings and whatnot. The last point is that using such proprietary ICs really does limit the scope of what improvements can be done and reduces project accessibility to many people all around the world. In order for a power switching circuit to work, the circuit must be able to switch between power sources really, and I mean really fast. A voltage brownout, or a dip, is one of the last things we want for the power-sensitive electronics to experience. A microcontroller is here hence not an optimal solution, since the reaction time would need to be really good. It could be probably done this way too, sure, but I wanted to try to dip my toes into some digital electronics to solve this problem. The main components that allow us to switch between power sources automatically are MOSFETs, both N-type and P-type. Basically, N-type MOSFETs allow current to pass between the drain pin and the source pin when the voltage difference between the gate pin and the source pin exceeds a threshold. P-type MOSFETs, on the other hand, allow the current to pass between drain and source when the voltage of the source pin is higher than that of the gate pin by a threshold. This unique property of the P-type MOSFET allows us to build a bidirectional switch, which disables current flow from both sides when a voltage high enough is applied to the gate pins of the switch. However, in order to be able to switch between two sources, a diode is needed to stop the backfeeding of the circuit, since both sources need to carry the current to the main power rail. An ideal diode using some MOSFETs and transistors would be, well, ideal, but the maximum voltage characteristics of commonly available diodes and MOSFETs really don't allow for such a thing. In this case, a diode with a low enough voltage drop is also fine, as we will be running high voltage and low current for the main power rail. This circuit has a problem right now though. When the voltage from the adapter is just in the wrong spot, the MOSFETs can get stuck in a half-open, half-closed state. This is really not optimal, as this is one of the best ways to kill a MOSFET, especially when such a thing happens continuously. To block such cases, we need to first check if the voltage source has enough voltage to be able to use it properly. To do that, we can just use a microcontroller together with a voltage divider to measure the voltage. Then, by using an N-type MOSFET as a switch, we can allow the current source to be connected to the main power line whenever the voltage is ensured to be high enough. The problem with using a microcontroller is that it too needs to be powered by something. Even if they don't require much power, I would like to increase the standby time as much as possible. For this, we will be using a weird way to disable the power to the microcontroller when we don't need it. The circuit for that is as follows. The enable pin of the regulator powering the microcontroller is able to be pulled high by three different sources. First, if a valid enough power source is connected to the adapter, the enable pin is pulled high, powering up the microcontroller. Second, a power button connected to the main power line is able to pass current through the enable pin, again enabling the microcontroller. The last source is the microcontroller itself. The microcontroller, to keep itself alive, can pull the enable pin of the regulator high, and when it deems it's okay to be shut down, it pulls the pin low, cutting the power to itself in the process. So that these three inputs don't interact with each other in weird ways, diodes are used. Additionally, you can spot some Zener diodes throughout the circuit. These Zener diodes are there to clamp the voltages to safe levels. For example here, at 20-ish volt main, rail potential also means that the adapter needs to be at least 20 volts as well. I could try to source or even make a 20 volt barrel jack adapter, but there is a better solution, namely these kinds of USB-C power trigger boards. The simpler ones can communicate with a USB-C power brick and try to get a specific voltage. When set to 20 volts, it tries to request 20 volts, and when it fails, it goes to the next possible lower voltage. To charge the battery, I decided that a constant current, constant voltage regulator would be a good enough of a choice. Connecting the input of the regulator to the switched adapter power allows the battery to be charged when the adapter is connected. You could also additionally add another MOSFET controlled by the microcontroller to turn on and off the battery charging. There is probably also the possibility of controlling the voltage and current using the microcontroller, but I would like to dive into that idea in a later time. Well, all of this is just a theory till now. Let's see if this thing actually works, shall we? For prototyping purposes, I created the circuit on some perf boards, which I am proud with the compactness and the looks of them. Of course, if the prototypes work, the more logical thing would be to design a two-sided PCB to make the whole design more compact, which I will probably do in the future. For the initial test, I am using a variable power source as the replacement to the battery in order to be able to monitor the current draw more easily. We can again connect this, hopefully nothing blows up. And something is current limiting. So we are right back after the incident. This regulator, although the datasheet says that it should be okay until about 25 volts, just blew a short-circuited at 18 volts. And as I really don't want to order a new one and wait for that and let this project just be delayed for even longer, I replaced this one with one I already had and added some diodes here and also under the board to hopefully lower the voltage a bit. I know that this really isn't optimal, but just for testing purposes it should be fine. I will optimally replace this regulator with something else. I have a variable voltage and variable current power supply of the camera, which leads are here. I have it set to a max current of 30 milliamperes or 60 depending on the voltage. And we also have a USB-C connector here that is able to supply 20 volts. And this board here is the PD trigger switch. Depending on the switch position, you can get variable voltages from the USB-C port. I have it set to 20 volts here. And as you can see, it negotiates and gets to 20 volts. If we probe the positive and the negative terminals of this, we should see about 20 volts, which is close enough. And as the chip uses a linear voltage regulator on board, it gets pretty toasty, so I added a heatsink here and a casing so that nothing shorts out or I accidentally touch the switches or something. So let me put the casing on. Now we have the MOSFET board, so the one that is going to switch the power sources, and also the voltage regulation board and the like on signal generator. I also have here a 5 amp 5 volt voltage regulator, so DC-DC buck converter or whatever you want to call this. This is going to be used as a load in conjunction with this. It's just a simple power bank, and we will try to charge the power bank using this circuit. Yep, so here we have the pinouts, and I'm going to be connecting these two depending on the pinouts. So let's start. This is our enable pin, which we in this case can actually plug in directly into the output of the voltage regulator as a test. Normally we shouldn't be doing something like this, but the circumstances just don't line up, and this is our switch. So I'm going to turn on the voltage regulator power source, and I'm going to set it to about 17 volts. So hopefully nothing should blow up. The sparking was probably from the capacitor charging up, but here we have output voltage, which is nice, so we can measure it. So optimally we should have around 17 volts here on the main voltage output line. I'm going to measure it from here since it's directly connected to there. Yeah, so around 17.26 volts, which is exactly what I have set on the adapter. You can also cross-check it right here. We have near zero voltage drop there. And the voltage regulator should be outputting something. We can measure that too. Or not, because it's not enabled. Yeah, I forgot that. So we can enable the regulator. Now the power source entered constant current mode because this regulator is also active. And as I said, I have it set to 5 volts, but it's outputting 3.8, so I don't know what the problem is there, but when I connect the USB-C adapter, optimally nothing should change, since we didn't allow the adapter voltage to pass through here. So yeah, we still have 17.2 volts. We have here still 17 volts, but now I'm going to enable the flow of current through this MOSFET and diode combination. Now the off-camera power source is telling me that no current is being drawn from it, and here we should optimally see 20-ish volts. Yep, so 19.4. This means that the regulator, so this whole circuitry is functioning properly right now. You can also theoretically check the output voltages, but I mean, this is a much beefier power regulator, so there shouldn't be any problems charging this. Yeah, we should be seeing around 5 volts here optimally. Yeah, 5.2. So as you saw, the power management circuit works fine as planned, although with some incidents along the way. As I also was working on the project, I also realized that the usage of the ESP32, checking the input voltage of the USB-C was not necessarily necessary. So I will be addressing that in the following videos, where I will also focus a bit more on trying to find a solution for a BMS and a battery charge level indicator, which is essential for a laptop. Explain how the keyboard and the trackpad is going to be connected with some custom USB HID code, design the internals of the laptop, print them with a 3D printer when I have one, create custom PCBs, which I have been learning how to do in the last few weeks. So I hope you liked this video. If you have any suggestions, feel free to just comment them. You can hopefully find the schematics and the parts I use for this specific build in the description down below, hopefully on my GitHub repository. And thanks for watching, and I will see you in the next video.